Hello and welcome to the second part of lesson 2. In the first part we covered stress-strain diagram and kind of going through the different phases of the stress-strain relationship, the linear, elastic, and then the plastic. So in this part we'll just cover some attributes that you can analyze for a stress-strain diagram of a material, and also kind of have a little deeper understanding of what happens when the material is loaded and unloaded, and the ability of material to absorb energy. We have seen in the first part. So the elastic region, linear relationship, then the end of this linear relationship, the proportional limit, and some materials you cannot really find the end of the elastic limit, so you represent it with the yield stress, and then you have the yielding, and then the hardening here, and we'll see why it's called hardening, this region, and then once you reach the ultimate, you go to fracture stress. So the first thing we'll kind of start to learn when we look at a stress-strain curve is how brittle or how ductile is a material. So if we want to define what does it mean to have a material to be ductile, it's by looking at how much deformations it had after the yield up to fracture. So the longer this distance here, or the deformation, what we call it here, also represented as strain, the more ductile it will be. So for example, soft steel here, with less amount of carbon added, it is characterized as more ductile than other type of steel that's shown here in the graph. So we add carbon to increase the proportional limit of this material, or increase its elastic region of it. All of them still have the same stiffness, so that's something we have to pay attention to. All of them have the same E. Steel, regardless of what type of steel we're dealing with, it has the same Young's modulus. Just the more carbon you may add, the more proportional limit you push it further away, so more deformations and it can take in the elastic region, but the slope or the stiffness of that is still the same. Structured steel, add more carbon, you push higher the proportional limit, but the down term of that is you make it a little brittle. Add more carbon to be like a hard steel, that now is more brittle compared to the ductile here, soft steel. One thing we can see here still in the hard steel, we can kind of differentiate between the ultimate stress and the breaking or the fracture stress. In some other brittle materials, you cannot differentiate between ultimate and fracture, so the fracture happens right away or pretty close to the ultimate stress. Another thing also you can see, but not from the graph, you can kind of, if you want to categorize brittle and ductile, is by looking at the fracture surface here. So if you look at the ductile, you will see the shape of the fracture is more cone shape, while brittle materials show more flat surface of the fracture section here. You will find that it's kind of granular. This one here is less granular. Another thing is what we discussed last time, the cone shape here represent that the failure is caused by shear failure, but brittle materials are probably caused by or because of that flat perpendicular fracture surface to the longitudinal line of the member. That's a clear indication that it is a tensile failure. So tension was the cause of failure here, while shear was the cause of failure here. So to summarize, it's kind of you have to use indications, look for indications to know if you're dealing with what level of ductility you're dealing with. So neck shape here is one indication of ductility, and also the level of strain or the amount of deformation that the material can take on between in the elastic region or the yield up to the fracture. So for some elastic materials, that amount of strain, so the strain at the failure is around 200 times the strain at the elastic at the end of the elastic region. It's a lot of, a big difference here. So that's the difference between ductile and brittle. They're used at different applications in life, but it's good to start categorizing ductile and brittle. Ductile, you have a lot of indication that the material will fail because you have that nicking, so you can see it. But brittle is just sudden. So in the lab, you'll actually like no indication of shot. Boom! We'll hear a big bang, and the material fails. So of course, when we start building things, we want to build with ductile material, not brittle material. We want to see the beam is deforming, so we can actually evacuate the building, and we can see warning signs before, rather than actually seeing it's just sitting and then boom, you see a fracture and the failure of the system. Another thing we'll look at is the plastic behavior, because sometimes you cannot control that the material will still be in the elastic region, so your deformation might extend you to be in the plastic region. So when the material is deformed beyond the elastic region, you see here the loading happens, and then of course now you're going into nonlinear plastic region. But when you let the load go, so it didn't reach yet fracture here or rupture. So when you let the load go, you will see that the material actually tries to go back a little and regain some of that deformation. So you'll see that this is the unloading path here from point C all the way to point D. So from experiments, they noticed that this the slope of this line of unload path between the stress and strain is parallel to the load of the elastic region during the loading path. So if you draw a line parallel to this line, you will find that you end up with this point here, meaning that now at zero load you have that permanent deformation AD, or permanent strain AD. So now your material will start like that. It will be, once you load it, and then it goes back down, not to the original length, but a little bigger. That difference is the permanent strain and deformation. Now let's say the material under cyclic loading, it will be loaded in another cycle. So it will start with this existing strain, and it will be loaded again, following the same path, linear path of that. But you will see here that when it goes, it doesn't end up linearly here with that old elastic limit that you had, or proportional limit you had before. It actually could keep going linearly until it hits approximately the same plastic curve it had before, and then it will start merging into that plastic curve that you have. So the idea here is that you're making the material harder. You're increasing your yield limit. So instead of staying here, you did that on purpose. Kind of, you made the material go into the plastic or harden and let it go back, have some permanent deformation, but when it's being loaded again, you will have more ability to load it in elastic region by lifting up your yield limit. But the downturn of that is your ductility now is reduced. So that distance here is not the same as this whole distance here between the yield and rupture when it didn't have any plastic deformations yet. But now your ductility got reduced. So there is a trade-off between the level of your yield limit and the ductility of the material. If you want to have a higher yield limit for a material, then you have to harden it, which reduces its ductility. The last thing we'll cover today is in this part is what's called strain energy density, which kind of also let us understand what's really happening when a material is being deformed. So strain energy, we refer to here as uppercase U, is the work done by a load P when it's applied on a sample or a material. Work by definition is force times distance. So when we load, the distance that the load travels is initially linear. So you put 1 pound, you increase by, let's say, 1 micron, and you keep doing that linearly, but at some point it's not linear anymore. So to find the accumulative energy or work you have done with the force, you have to do that integration here. So that's the strain energy, the integration of P times dx. Just one thing to note, that's not the strain stress curve. It's the force P and deformation diagram. So it's kind of related to the stress strain, but this is the force, not the stress, and this is the deformation, not the strain. Because we are calculating the work here. So we're looking for the P, the load, and the distance it travels or the deformation it makes. Now another thing we can calculate here is the strain energy density. So kind of if you think about density, the regular density we know is the mass divided by the volume. Now strain energy density is the energy or the work divided by the volume. So this is why we call it density here. So just dividing U uppercase here by V. Now V is fixed, so I will put it under integration here to do something very cool here. So V is equal to the area, cross-sectional area times the length of the member. So P over A, guess what? It's stress. Dx over L, deformation of the original length, is what? Guess what? It's the d epsilon, or the strain. So you end up here with the integration of stress times little strain that you have. So when you do that integration, you end up with the area under the stress strain curve, which is pretty cool. I mean, you have already the stress strain curve for the material. You can calculate now the amount of energy that which moves us to another definition of strain energy density, is the amount of energy that a unit volume of the material can take to result in a specific strain value. So what we're looking at now is we can quantify the amount of energy that a material can take under a load to cause a specific deformation here. So we are more interested, or if we're looking at a strain energy density here, we're looking more into the case when it's elastic, so amount of energy that it can take up to a point where it can actually regain all the deformations back, so the elastic region here. This value of the strain energy density, we call it UR, or the modulus of resilience. So it indicates the ability of the energy that the material can absorb without permanent deformation, which is also important. I want to know how much this material can take, but at the end, I don't want it to be deformed when I remove the load. So, and then the other value of strain energy density that also I can calculate, and instead of limiting the integration to only the elastic region here, I can do the integration for the whole area under the whole stress strain curve, and that will give you the modulus of toughness. So how tough is the material is how energy it can take on and on and on until it rupture or breaks. So of course we're not talking here that how much it can regain elastically. We're talking really about finishing this material, this member, is calculating how much energy it takes to break it up. So these are this is the stress, the strain energy density, and it's basically the area under the stress strain. We understood kind of the very fast derivation and the theory behind it. And we all are interested into the two possible values of strain energy density, the modulus of resilience and modulus of toughness. one thing to note here, resilience means is the ability of something, can be a system, to take on, to be disrupted by an event, but still go back to the original state before that event. So when we call always like infrastructure resiliency, or someone is resilient, is when there is a calamity or big event causing disruptions in the life of that person or that asset, they can quickly, how quickly they can go back to the original state before the disruption. This is called resilience. So kind of relevant also to what we're talking about here. One thing also to note here, which is also cool, is that we can feel that energy. So if you are loading an element and it goes into the plastic, this means blindly now you can know when you relieve this material from the load, there will be plastic deformations permanent. But when you let it go, that load to unload now, that energy here, that triangle here, is used to recover the elastic deformations back. What happens here then? This energy that kind of you put in the material, elongated, you gain some of that energy to bring back the material and regain some of that elastic deformation. What happens to that energy that you put in the material? So that energy translates into heat. So in the lab, when you do the tests, when you hold the material after fracture, now there's nothing regained. Everything now is in the material until it breaks. That you will hold the specimen and you'll feel it's hot. If you're not careful, actually it can burn you. So it depends on the modulus of toughness, right? How big it is. So whatever energy or work you put into deforming a material and it was not recovered during the unloading, it will be transformed into heat. Some cool also things here to discuss are the implications of material strain energy. So for example, in buildings for civil engineers, earthquake engineering. So earthquake comes with a lot of energy. Shaking the ground and the loads in the building cause that mass cause dynamic loading of the building. So the idea here that in earthquake engineering and structural engineering, we would like to predict the behavior of the building. So what happens is we create weak points in the building on purpose. That these weak points, what we call links, will absorb that energy of the earthquake and go in and behave in the plastic region. So after the earthquake, they will be completely gone, kind of deformed, but the building still integrity is still maintained in high degree, and people will not be harmed. So you're kind of channeling the energy of the earthquake to where you want it to go and controlling the failure here in the way you want. Another thing to also think about for mechanical engineers is designing a car. So we always feel bad when you have a car accident and having that collision in the front, destroying the front of the car. It is actually designed on purpose to do that. We could have actually make the car tough or a little elastic, but this energy, if it does not cause that collision or damage to the car, goes where? It goes to the rider, the driver. So for the safety of the rider or the driver, we are channeling that energy of the shock or the collision into the body of the car, into the front part, up to the limit that makes still the driver safe. So there are a lot of applications of energy and application and or input into deforming materials, and they have a lot of impact on the safety issues of the structures or the systems we design. So that's the end of this part. So we learn about the kind of more things you can leverage from stress strain curve. We learn about ductility versus brittle materials. We learn about strain energy density and their implications in real life examples. Thank you for watching, and I will see you in future videos. Thank you.